All right, let's finish up chapter 7 then. Quickly, we'll talk a little bit about what non-conservative forces are, now that we know what conservative forces are. And then we'll also go over some examples kind of showing all the different stuff that we've covered throughout this chapter. Okay, so we know then conservative forces are forces that conserve mechanical energy, right? So again, we have mechanical energy is given by our total amount of kinetic plus potential energy. And we know that conservative forces conserve mechanical energy. So of course, non-conservative forces do not conserve mechanical energy, right? So essentially what we're saying is, again, when we have only conservative forces acting on our system, we have to maintain this total amount, right? But when we have non-conservative forces acting, this amount can change, right? So we know that when we're talking about the work done by conservative forces, this has to be equal to minus delta PE, right? Minus the change in potential energy, right? That's where the conservative forces get their work, get their energy from. They take the potential energy. And so then we can say when we have both conservative and non-conservative forces acting. So this now covers all the different possibilities that we could have, right? We can say that this must be equal to our net work being done, conservative plus non-conservative. There's nothing else that it could be. And so this will now be our change in kinetic energy, right? So this does change our formula a little bit. We can then say for our work from non-conservative forces, this is going to end up then being, if we plug this in here, move it over, this is then going to end up being the change in kinetic energy plus the change in potential energy. So if you ever gain or lose some of your mechanical energy, right, then it's basically just a result of these non-conservative forces acting. So whatever the changes in this total mechanical energy is, however that changes, that's got to be the amount of work that was done by non-conservative forces. So that leaves us with our now general formula for when we have a system with both conservative and non-conservative forces acting. We can write this. It looks very similar to what we had before. Kinetic energy initial plus potential energy initial plus the work by non-conservative forces has to be equal to our kinetic energy final plus potential energy final, right? Okay, and so then again, for our case, this will usually be friction, right? So friction is going to oppose the motion of some object, right? So if I have something sliding along, friction then pulls it backwards and slows it down, right? So we can see how when we had that box sliding down a ramp or something like that, right? If you add friction to the situation, obviously now the box will be moving a little bit slower than it otherwise would have, right? So this is usually going to be friction. And so this will usually be then friction will always be doing negative work, right? Because it's always going to be acting in the opposite direction from the actual displacement of our object, and so we'll end up with slightly less kinetic and potential energy than what we had when we started, right? Okay, so now we kind of have all the basic concepts down for chapter 7. Let's go over some examples and make sure we can kind of see how this stuff all ties together. So for our first example, we're going to say that we have a box that slides along a conveyor belt. So we're going to say a 30 kilogram box is being pushed down some sort of, not pushed down, I guess just pushed along some sort of conveyor belt or some sort of assembly line is pushed along assembly line for 0.8 meters, right? We have the force exerted on the box is 120 newtons, and there is a 5 Newton frictional force opposing the motion. And so we want to know a couple different things, right? So we've pushed this box along. We've got our box that's on this. It's on some sort of conveyor belt or assembly line or whatever it is. It's just being pushed along some surface. there is a applied force to it of 120 newtons, but there's also this frictional force that we have of 5 newtons kind of opposing the motion. And so we want to know a couple different things. We want to know what is the work done on the box. We want to know how fast is it? How fast is it moving after being pushed? And then we also want to know if I push it with this 120 Newton force for a while and then let it go on its own, how far will it slide on its own? So we're going to assume that we still have that same 5 Newton frictional force. How far will it slide on its own after being pushed, right? So what's the first thing we want to know? We just want to know what the overall total amount of work being done on this box is, right? So we know we have 2 different forces on it, right? Well, we have 4 different forces, right? If we really draw our free body diagram. Here's our box sliding along some surface. We have gravity, we have the normal force, we have some sort of applied 120 Newton force going in that direction, and then we also have this 5 Newton frictional force opposing that motion to the left, right? So the displacement then is going to be forward 0.8 meters. So if these are my forces, right, normal force is not going to do any work, gravity's not going to do any work, that should make sense. We're on this nice level surface. The box is being pushed forward, so that will do some work, right? So we'll have 120 newtons forward, we'll have minus 5 newtons backwards. So this will be my net force, 115 newtons. And then the distance is times 0.8 meters. And this ends up being 92 joules worth of work that has been done on our box, right? So we have this, and the next thing that we want to know is how fast is the box moving after it's being pushed? Well, so if this is the network, right, this has to be, here's my net force, so this is actually the network. So we can say that 92 joules is also equal to the change in kinetic energy, which in this case will just be 1/2 mv squared, right? We're assuming it was starting at rest. We didn't have any other information to assume otherwise, so we're going to say it started at rest. So we did 92 joules of work on it, right? We had 120 newtons pushing forward, we had 5 newtons pushing backwards. 92 joules was our net work done. This must be how our kinetic energy changed. This 1/2 mv final minus 1/2 mv initial, but of course, there is no initial speed, so that term is just 0. So now we can just simply solve for v. Right? So we have v is equal to square root of 2 times the net work divided by m, right? So we know that this is 30 kilograms, 92 joules, and what we get for our speed is about 2.5 meters per second. Okay, so this answers the second part, right? We know how much work was done, 92 joules. We know how fast it's moving. So let's see how far will it slide on its own after we start to just let it go, right? So we pushed it for 0.8 meters, and now we're just going to let it slide. We still have this 5 Newton frictional force acting on it. So there's a couple different ways that we can think about this, right? And all of them will be correct. So we can say, okay, right now, how much energy does this box have, right? It has 1/2 mv squared worth of kinetic energy, which we know is 92 joules. And so the force acting on it at this point as it's sliding along, we don't have this applied force anymore. We only have this frictional force pushing back on it, right? So in other words, in order to bring this box to a rest, the frictional force has to do negative 92 joules worth of work. So you can just simply say, as long as the magnitude of friction, so we can simply say 92 joules equals the frictional force times the distance, right? And so then, of course, we can solve for distance this way, or we can think of it with this formula that we just derived here, right? Just a few minutes ago, talking about this, we can use our kind of energy, but we have, it's our conservation of mechanical energy, but we're not actually conserving it this time because we have non-conservative force of friction acting. We can say, what did we start with? We started with 1/2 mv v squared worth of kinetic energy, and then we subtract the work done by friction times the distance, and then this equals, there's no potential energy, and then after it comes to a stop, there's no potential energy, there's no kinetic energy, so that would be 0, right? And so either way you do it, you'll end up with the same result, right? So overall, you'll have, because this 1/2 mv squared is 92 joules as well, so just keep that in mind. That's why these two formulas, you can think about the same thing. You can either calculate how much, you can either say, okay, how much work does friction need to do to bring it to rest, or you can think of it in terms of just our looking at our general formula for how our energy changes when we have both conservative and non-conservative forces acting, right? And either one will get you to the same result. So D is then equal to 1/2 mv squared divided by the force of friction, which we know is 5 newtons. And if we plug all this in, what we get is 92 joules divided by 5 newtons, gives us a distance of 18.4 meters, right? So that is how we would do that one, right? So we're given the forces, we're just kind of asked to see how this box is going to move with using energy considerations, right? We could have done it with our Newton's laws, we could have figured out the acceleration and all that, but we can actually do it in a little bit simpler way by using this energy stuff that we have learned about now. Okay, let's do another couple examples. We'll say now we have a toy car is pushed against a spring and compressed a distance of 5 centimeters. So we've got like some little Hot Wheels car or something on a track, and we're going to push it up against a spring and then see how far it's going to go after we release it. Okay, so we're going to say the car has a mass of 0.15 kilograms. I guess this is a pretty big Hot Wheels car, as it turns out. And the spring has a constant of 470 newtons per meter. So again, we just got this car on the spring. We're going to push it in, then we're going to let it go, and we're going to see how far it can go. And what we want to know is how fast will it be moving after we release it, and how high of a hill can the car climb. So we know how fast it's going after we release it, right? We've kind of compressed it up against the spring, like this little spring-loaded Hot Wheels car. We're going to let it go. We're going to see how fast it's going, and then we're going to see how high up of a hill could it climb and actually make it over, right? So we've got some situation that looks like this, right? We've got our spring with some little platform here, and we've got our car, right? And then we've got some sort of hill that this car is going to go up. We want to know how high can it make it up before it either starts flying back down or actually is able to make it over the cliff. But basically, what's the maximum height that it can reach if we have it like this? So this is what we have here is we have the spring force acting on the car at first. We're going to assume we don't have any information about this, so we can assume that this track is frictionless, or the wheels on this car are nice and frictionless, so it slides along or rolls along very well. And then, of course, we have the gravitational force that's going to be pulling it back down the hill, right? That's kind of that's why it can't just go up as high of a hill as it would like. And so we have the spring force, we have gravity, and that would be it, right? So we only have conservative forces in this case, so that makes our problem a little bit simpler. So for the first part, it's very simple. We have 1/2 kx squared of potential energy, and we are going to convert all of this to kinetic energy, right? Once we've pushed this spring in, once we release it and let the spring go, there's no more potential energy stored in the spring. All of that potential energy has been transferred to the kinetic energy of the car. The car, we're saying, hasn't gone up or down any hills yet, so we don't have to worry about the potential energy, gravitational potential energy just yet. So we can solve for V very simply. 1/2 cancels out. Square root of k x squared over m, and this is going to be equal to about 2.8 meters per second, right? So we have 470 times, make sure you remember this is in 5 centimeters, so it'd be 0.05 squared divided by 0.15 kilograms. Take the square root of that, you should get about 2.8 meters per second, right? And so the next part we want to know is how high of a hill can the car climb? And you can do this one of two ways, right? You can either say, let's convert the kinetic energy into gravitational potential energy, or you can say let's convert the spring potential energy that we started with at the beginning and convert that into gravitational potential energy. And either way will work. Either way you can solve for h. The numbers will end up being the exact same, right? This velocity was based upon the idea that we started with all spring potential, then we converted it to kinetic energy of the car. Now the kinetic energy of the car is going to be converted into gravitational potential energy. We're going to see how high it can go, right? What's the maximum height that we can reach? Or we can just think of it as we're just shooting this car up the ramp with this spring, and so we're going straight from potential spring energy to gravitational potential energy, right? And either way will be just fine. Either way you can solve for h, and what you'll get here, I just did it using the spring, so say 1/2 kx squared divided by mg, and what you should get is a height of about 0.4 meters, right? So in other words, about 40 centimeters is the maximum height that this car will reach. So as long as the crest of this hill is 40 centimeters or less, this car will be able to make it over. If it tries to go up higher than that, it'll stop and start rolling back down. And then of course it will hit the spring, have some kinetic energy that converts into potential energy, and then just keep bouncing back and forth, right? Obviously in real life, there'll be some friction, right? It'll slow down. But if you approximate this as frictionless, this is actually a decent approximation for how high this car will be able to travel, right? Okay, let's do one more example. Okay, let's say in this case we have a real car, not a toy car, so a 900 kilogram car driving up a 5-degree incline at 25 meters per second, slams on their brakes. And so we want to know is how far it's going to slide up. So we're going to say the tires lock up and the car starts to slide. If the coefficient of kinetic friction, u sub k, equals 0.7, how far does the car slide before coming to a stop? So that's one thing we want to know. Then we can also say how far would it slide if it were going 20 meters per second, right? So those are two things that we want to know. We want to know, okay, it's starting at 25 meters per second, slams on its brakes, it's going up an incline, so that does change things. We have to make sure we keep track of all the implications of this. So we slam on our brakes. We have this coefficient of friction, reasonable for tires on pavement. We want to know how far does the car actually slide before it comes to a stop, right? And so then, of course, we can do it again. We'll derive one formula for how far it slides, and then we'll see what the difference is between 25 meters per second and 20 meters per second. So just for reference, this is roughly a difference of about 10 miles an hour. This is about 50 miles an hour. This is about 40 miles an hour, right? So that's kind of about the the difference that you're dealing with in these speeds here. Okay, so first let's look at what we have. So we do have both conservative and non-conservative forces acting, right? We know we start with some kinetic energy. Our car is moving, so we have 1/2 mv squared kinetic energy at the beginning of this problem. Then we know friction. We will do some negative work, right? Our potential energy, we can go ahead and set to 0. We're going up a hill, right? We are going up an incline, so we'll end with some potential energy, but we may as well say that we start with 0 potential energy. Again, where you define 0 potential energy, that's your choice. Just make sure you're consistent with it. I'm just going to say that the car starts at 0 and ends up with some. If you want to say it starts at negative and ends up, that's okay. You just have to, it makes it a little bit trickier to write the equation, but I think this makes the most sense to me. So this is what I go with. So we have 1/2 mv squared minus mu times the normal force times the distance that the car slides. This will be the amount of work that friction does, right? It's negative work. It's opposing the motion of the car. It's mu times the normal force times the distance that it slides, right? So here's my kinetic energy initial, my potential energy initial is 0, and then here's my work from non-conservative forces. This is then equal to my kinetic energy at the end, which is 0, plus my potential energy at the end, which is going to be m times g times h, right? So it's sliding up this incline, so we do need to draw this out and make sure we understand what's going on. So the total distance that it goes up, the vertical distance, is all that we care about for the gravitational potential energy, right? We can slide this car horizontally back and forth as much as we want, and the potential energy never changes. But when it goes up this slight vertical distance, right? So this h is different from d, but we can kind of draw our picture. We can see how they are related to one another using our trig skills that we have. So our picture looks something like this, right? We have our car. It's slammed on its brakes. All the forces that I have acting on my car, then right, so we have this 5-degree incline here. It's going to slide some distance d before it stops. So my forces now are, we have gravity, we have the normal force, and then of course we have friction, right? So let's figure out what this relationship is first between h and d. So the vertical distance h here is going to be related to d. We can say that h is actually just going to be d times the sine of theta, right? Sine of theta equals opposite over hypotenuse. So opposite over hypotenuse, multiply by the hypotenuse. H is just going to be d sine theta. So this is good because that now puts another term of d in our equation, which is what we want to find, right? We want to find what the actual displacement was of this car sliding. So we can rewrite this a little bit. The other thing we need to figure out is what do we plug in for this normal force, right? So the normal force in this case is going to cancel out this component of gravity here. And so as we know, we've done this before, right? This angle here is also theta. So the normal force is canceling out mg cosine theta. So the strength of the normal force is equal to mg cosine theta. We know what the theta is. We know it's this 5-degree incline. Oops, I'm off the page a little bit. Okay. So we have this situation here. So we can plug in our normal force, we can plug in our height, and then we should have just this displacement, the actual distance that we slid up this hill as the only unknown variable. So let's see, 1/2 mv squared minus mu mg cosine theta times d equals mg d sine theta. So we know the theta, we know the mass. We can assume we're on Earth. We're driving our car. We don't know this displacement, this d, this distance that we went. We do know the mu. We do know our initial velocity. So we just have to rearrange this for this distance. So we can say, right, 1/2 mv squared is equal to mg sine of theta. I'll just factor out this d right away. Mg sine theta plus mu mg cosine theta times d. Solve for the d, divide both sides by this whole mess here. So we have the distance is equal to 1/2 mv squared divided by mg sine theta plus mu mg cos theta, right? And so actually we do have a term of mass in all of these terms, so we could cancel out this mass as well if you want. You don't need to bother to plug that into your calculator. Just make sure to cancel out in all the places, or don't cancel out at all, right? So yes, when you do this, right, we know our 5-degree incline, 9.8 meters per second squared, 900 kilogram car. Again, the mass which we cancel out though, 25 meters per second squared for our v squared. The distance that we slide is about 41 meters, right? Now if we do this again, but we plug in, if our v is 20 meters per second, how does this change this? Well, you can go back, you can plug your stuff in. So we're only traveling 5 meters per second less, but the distance that we're actually traveling, as it turns out, the distance that we slide after we slam on our brakes, in this case, it's only 26 meters. So the ratio of our speeds, right? We had 25 versus 20, but the distance that we actually traveled was a lot less, right? We're almost half the distance. We slid almost half the distance by just dropping 1/5 of our speed. So the way this works is you can see it like this, right? 41 meters is how far we go, but the distance that we slide, as you can see, is based upon the work that we need to do to stop this car, right? Friction is doing work to stop this car from sliding. And so the more energy this car has, the more the work needs to be done. And the energy is based upon the speed squared, right? So a small change in speed can actually lead to a pretty large change in how far you actually stop, right? What the stopping distance of your car is going to be. So this is again why in school zones might seem silly, but when you drop from 35 miles per hour to 25 miles per hour, that's going to be an even, that's almost more than half of the stopping distance between those two speeds, right? It might seem like a small change while you're driving, but a small change in your speed will allow you to stop much, much more quickly, right? And allows you to drive much more safely. So that's kind of the reason why this is, right? Energy is based on speed squared. So a little bit more speed gives you a lot more energy, and means that the distance that you're stopping distance is actually much, much larger.